So as promised, here's an example that uses the printout in order to answer all of and plus more questions regarding the regression equation that we just looked at. So irrespective of whether this is for the exam or not, interpreting this printout is going to be very important towards learning this concepts or these concepts. So this is a typical Excel printout for a simple linear regression. Immediately you should know that it's a simple linear regression, because if you look at this part of the table at the very bottom, you only see two words or two variables, the intercept and an x variable. So there's only two of them, and therefore this is a simple linear regression. If I can jump ahead a little bit to chapter 14 and show you an example of that. Same printout, I added in another two variables to the problem. Immediately you can see that this is a multiple linear regression, because it has an intercept as well as a first x, a second x, and a third x. So immediately when you see a printout, you should be able to tell if it's a simple or multiple linear regression. So you can see right away that it's a simple linear regression here. And one of the questions that will always be asked when this printout is given is state the regression equation. The regression equation is right there under the column called coefficients. So this is the coefficient for the intercept, and this is the coefficient for the slope. So as we've derived it before, it's going to be 15.84 minus 0.13x. So immediately you should know what the regression equation is. And of course, a subsequent question would be calculate the predicted value of y, given that f is or x is some value. So you're able to plug into a value into x in order to derive your expected value of y. So jumping back to the top, the regression statistics. First line, since this is a simple linear regression, you're going to see the r, and so this is a value that we saw together. This says that it's a strong relationship, but we don't know the sign. So the sign is going to be the sign of the slope. So whatever the slope is here, negative. So in this case, it's a negative 0.95 value for r, meaning it's a strong and negative relationship. Only in simple regression can you square this to come up to the r squared value. So here we have an r squared of 0.9, meaning 90% of the movement of y has been explained by x. So that, just to write it down, 90%. And for once, the handwriting actually turned out to be decent. We're going to skip the value for our adjusted r squared for now. We're going to look at that in a later chapter. The standard error is right here. This is your standard deviation of the epsilon, or the error terms. In this case, it's 0.65. It is equal to the square root of MSE, which itself is equal to the square root of SSE over n minus k minus 1. You have the number of observations here, and this tells you that it is quite a small sample size. So when you're testing, usually you should use the t-stat. Looking at the ANOVA table, the analysis of variance table, you have the most important column is right here. This is sum of squares. That's what SS stands for. The first line is the sum of squares of the regression. So this is your this is your SSR. This is your SSE. This is residual. Residual is another word for error. And finally, you have the total. This is your SST. Remember, SST is equal to SSR plus SSE. Very key and begs to be repeated. Next, you have what is called the mean sum of squares. So essentially, this column is derived simply by taking a value here and dividing it by its degrees of freedom. These degrees of freedom are k, n minus k minus 1, and n minus 1. That's how we got 1, 6, and 7. So 22.98 divided by 1 obviously is itself. 2.57 divided by 6 is 0.3. So we use this in order to derive the critical value, the test statistic for the F. So immediately you should be able to tell if this model is significant, because as you know, the value for F is MSR over MSE. And so look at this value, it's 53. Anything larger than 3 is usually significant. This is many multiples higher than 3. And so this is a very significant model. And then you see the last column, significance of F. Essentially, it is the p-value of F. Look at the p-value of F. I actually purposely left it as 6 decimal places. So it is quite small, essentially equal to 0. And so P is going to always, in this case, going to be less than alpha. And therefore, when this happens, you reject HO. Rejecting HO means that if we were conducting a test for R squared, it's going to be rho squared is equal to 0 and rho squared is greater than 0. And so when we reject HO, we're going with this. And therefore, we know that a regression equation is significant and the R squared is significant. So immediately you can tell just by looking at the F test right here, the test statistic, it's large. And if you weren't convinced, look at the p-value, which in this case is extremely small. Okay, I'm purposely leaving some of these equations on the board here just so that we can discuss them a little bit later. So we've already discussed what the coefficients look like and what they do. The standard error is nothing more than the standard deviation for each term. So in this case, this guy is the standard deviation for B0, and this guy is the standard deviation for B1. So this is the one that was very difficult to calculate because it was involved in several other calculations in order to reach it. And so if you would like to test the slope of the line, you're going to be testing the significance of F. Is it significantly different than 0? Is this significantly different than 0? And so if you remember, the test statistic was B1 minus big B0, big B1 divided by SB1. And so in this case, negative 0.13 minus 0, I got this from the hypothesis, divided by, and SB1 is essentially this 0.02 right there. Okay, so when you do the ratio you see that I wrote now, you should get a value close to negative 7.33. Of course, you're going to get something a little bit different, I think around 6.5 or negative 6.5, because I'm using rounded numbers. So if the numbers were taken to more precise levels, you would get the value on the printout. So another trick, immediately you understand, or you should understand, what the t-stat column tells you. It's telling you the significance, the test statistic for each one of those variables. So in this case, you can see that this value is extremely large. It's greater than 3, twice as high as 3 actually, and therefore it is significant, and therefore the variable F is significant. So you can see not only did we prove that the model is significant, but we also proved that it's that the one variable used in the model is also significant. So the answer to this, both of these will always be in unison, meaning they will always give you the same result. If one rejects, the other rejects, and vice versa. You're also given on a full printout a p-value. So what is the probability of observing a coefficient this small or smaller? The answer is approximately 0. And so if it's 0, it means that p is going to be less than whatever alpha you're going to choose, and therefore you reject. And so that tells you that is a significant variable. So this way, looking at the printout, we've determined that the model is significant. We've determined that the slope is significant in two different ways. And then we have a 95% confidence interval as well as a 99% confidence interval in this case. And you can and you can see the significance of the variable because, as you can see, the upper and lower limit do not include 0. So as long as the interval does not include 0, 0 is somewhere here, that means the interval or the variable itself is significant. So this is a brief overview, hopefully a complete overview of what the printout would look like. If there's any advice I would like to give, and this happens very often on this particular exam, very easily you can receive a question that looks like this. Now this is a little bit of an extreme situation, but what I'm trying to show you is that you can probably solve for the blanks or fill in the blanks using only the information you see in front of you. And this is a very possible type of question where you have to use the information on the table in order to derive other parts of the equation. So if I were you, I would play around with this table extensively so that I can understand where the different values come from. And by extensively, I mean maybe about 30 or 40 minutes because I think it's pretty straightforward.